Sure. Awesome. Yeah. So this week, we'll be mostly talking about storage engines. The agenda was anyway shared. The architecture of S3 will be spilled over to the next week because no, I thought of it. I thought of putting in a very detailed discussion around two topics that I wanted to cover. So that would be much more. Basically, that would be much better than just going to theory and one brainstorming in between. So ensuring ki matlab we every code has some unique element of it. Like for example, Gravatar design was unique, and in this one also I'm trying to pull in something interesting. So let's see how it goes. So S3 design will be covering next week as part of spillover, but there will be one very interesting homework problem. I would really want every single one of you to put in a lot of thought on how would you design that. It's going to be really fun. It's a very simple but fun. I'll be talking about it at the end. So yeah, let's jump into it. And like always, we'll be talking about a lot of building blocks. So direct answer, no, but just understand the kind of decisions we have made and why we have made it. That is much more important because like you can very easily plug and play the overall decisions that we made versus direct answers. So yeah, let's start with the most common interview question ever. It's like distributed cache. I've not picked it up because of interview part, but because I wanted to have one storage engine that we cover that will that will encapsulate all the basic building blocks that I wanted to cover. So distributed cache is something that you might have heard a lot. You can replace cache with database and what here and whatnot because high level design of a cache or a DB which is distributed looks exactly the same. It's just that the way it is stored changes. For example, with distributed database, the storage would be persistent on disk. With respect to cache, it would be in memory. Like apart from this, nothing changes. Everything else is exactly the same. So I just wanted to have something as a foundation, something that I can talk about. So I just picked distributed cache as an example. So uh, in general, if we define distributed cache, it's like a simple a cache which is distributed across nodes. Like if you have used Redis, Memcache, Aerospike, any caching solution in general, it is typically distributed in nature. You can although spin up a single instance of it, but there are configurations available through which you can make it distributed across multiple nodes. Now the distribution when someone says distributed cache, it could be so the definition is very vague. Like it just is distributed cache, which means data is distributed. But what is really important to understand, like how the data is distributed. So I can have a distributed cache which looks like this. Like so, this is my cache C1, this is my cache C2, and both have same data. So this is similar to our master-slave replication of database. So any data that is written on C1 gets replicated in C2. Data is distributed. You can still independently query the individual cache. It is an example of distributed cache. Like, so data is distributed, but data is replicated also. So you can have like distributed and replicated, distributed and not replicated. So another example of non-replicated distribution could be like this, where C1 and C2 both are independent. There is no linkage between them. There is no like you just have like either data lies in C1 or it lies in C2. Right. So there would be, if you take the set intersection of both, it would be phi in case of distributed but not replicated, which means typically sharded sort of scheme. Yeah. While in the first one, it's like distributed and replicated. So whenever you're discussing this with someone at your work, when you're designing something, always get this thing clear. Would you want, or would we be designing something like should we be going with replicated as well or not? Like there are so many architectures here possible, so it would be always beneficial to like draw the fence around your question, like draw the fence around the system that you are designing, right? So typically when someone says about distributed cache, it's mostly about the second one and not the first one, right? So most of the cases it would be this, where one node is not enough to store all of your data. For example, if you are operating at, or let's say you just started a company, your Instagram, you just started a company and you have a cache cluster or you have a cache server. Obviously, you'll start with just one node. And then you've started caching user data, some recent posts by celebrities, in general, recent posts. You are caching a lot of stuff. When your number of users are growing, the number of content or the number of posts that you have is continuously growing, it would add a lot of pressure on your cache, because now the cache stores its data in RAM. RAM is very limited. So the amount of data that you can store in cache becomes very limited. So there would come a point where the storage of your cache would become a bottleneck. Right. So the storage of your cache is RAM. Your RAM would become a bottleneck. So in that case, what would you do? You would scale up. Right. So you would always do vertical scaling. But at a certain point, that vertical scaling would also hit a limit. Right. Translating this into relational world or a normal persistent database world, it would be your disk is becoming a bottleneck or your in-memory indexes are becoming a bottleneck, and that's where you decide to shard it, right? So typically that's how the evolution of any system happens. So you would start with one, do vertical scaling, and then once you hit that inflection point, get chalo, bang on, now I want to grow it horizontally, right? So because vertical scaling has limit, performance limit and whatnot, you would want to start scaling horizontally, because that's when you would be achieve true scalability, right? So now let's converge upon the functionalities that we would want to support. So bare minimum requirement, we'll just keep it very simple. Key value store, get, put, delete. All key and values get stored in memory. As simple as that. Now, but you see that Redis is also cache. It is distributed, but it has a lot of fancy commands. Like you would have sorted sets, you have your sorted sets, hyperlog, log, and whatnot. There are so many data structures available, right? So while building a cache, although we are just focusing on get, put, delete, but if you want to implement a lot of fancy features in your cache, all you have to do is just pick your interest or pick the data structure that you would want. For example, you can have a tree in cache, like you can do sorting, you can do in order, pre-order, post-order traversal, do rebalancing and whatnot. So at then it just normal C code which is running and has everything in memory, and that's all it is. Right. So you can have a lot of fancy thing, but the bare minimum thing that any cache would need would be get, put, and delete. Right. So all the fancy commands that you see in Redis, they are just like sophisticated data structures. Like they are none other than like normal. If you talk about linked list, if you talk about lists, they are just designed as linked list or arrays in memory. Trees are there, graphs are there. Full text search is another, like basically try data structure and whatnot. They are just these fancy data structures that we all have studied. It's just that implemented in C, being part of your Redis code base and basically exposed as normal commands of it. So you can have those data structures implemented, and it is nothing more than that. But the core three things that would definitely be required would be get, put, and delete. Right. So we'll just be focusing on that and then cover the high level aspects of it. So, so in general, this is a good thing. This is very important. Like if you want to implement a lot of things like this, so every key, because like if you see for Redis, everything is just a key and a value. Now this value could be a fancy data structure, that is different, but everything is just a key. So if you want to implement or if you want to support more than a key value store and have like sophisticated data structures, all you need is to have a type associated with every key. And this type would be nothing but the data structure that it represents. Right. So it is as simple as that. Just your key needs to have one more field called like type or something, which would represent like if it's a tree, if it's a graph, it's a try, if it's a hyperlog log, if it's a geodata or whatnot, right? So given that, you can then invoke the corresponding operation. So if you are implementing something like this, understand that the low level design becomes very important, because low level abstractions, low level design, classes, inheritance, right? Basically polymorphism, all of those things, because put in a tree could be append, or a put in a list could be append, put in a priority queue could be a different thing. So you might want to do those inheritance and polymorphism concepts here to have a good low level design, so that you don't have to rewrite a lot of stuff there. right? So that's how you'd be implementing it on the low level side. So you can go into, you basically you can make this thing as complex as you would want, but the simplest of all would be like key value, get, put, and delete. Right? That's the bare minimum that you would anyway have to support. Okay, chalo, let's brainstorm. How would you start approaching this problem? Like this is the only requirement, get, put, delete. It has to be a cache. Let's not worry about distributed, but let's first see like how would you implement a single, and this is exactly how you should be thinking. Although the question says that distributed cache, instead of worrying about the distributed part, let's first worry about the cache part of it. How would you implement a cache that supports get, put, and delete?
Hash map.
Hash map.
If it is concurrent, maybe concurrent hash map. I mean, too many requests. So concurrent hash map based.
Anyone? This is how you would storage. So basically, this is nothing but our storage. Like how would we store the key value pair, right? But what would your overall design would look like with respect to a single cache when you want to have? You'd have a normal user, then
web server with
let's say you have an API server,
which has get, put, delete APIs with I mean with the key as parameter, and we just read the parameter and do the operation.
And where the data would be stored? In the same API server?
Yes.
Okay. So data is also stored here. Let's say this is, no, instead of mapping it at database.
This is like the last thing. Maybe we'll have another server which will actually direct it to the proper server, which when we go distributed.
Yeah, when we go distributed, we can make things as complex, right? Okay. So you would have like your user is communicating with your API server and then RAM, right? So in the RAM, you'd be storing data in hash map. So hash map is typically Java way of saying like dictionary. So in Python word, it is dictionary, Java, it's hash map, but a generic data structure, what this implementation is called hash table. So hash table is the data structure and hash map is its implementation. Python dictionary, JavaScript objects, they are all very similar to that. So it's typically a hash table. So this is like a day zero cache for us. Okay, now let's start scaling this up. How would you scale this thing?
Add a load balancer before it, and which is like smart load balancer, which actually separates basically consistent hash.
So what exactly? No, you are directly jumping into consider. Wait. If they very because there are so many problems to uncover here. Okay. So what exactly? So here the first thing that we should be thinking about is what's or basically why are we requiring to scale this thing? What overwhelmed? What overwhelmed here?
We will get run out of RAM very soon.
So case one is we ran out of RAM.
Connections.
Okay. So the first thing is let's take one example is right. Let's say we ran out of RAM. Now, how would you solve this problem if we ran out of RAM?
Immediate thing is to just increase the RAM for that machine.
Okay. So then
scaling it.
Vertical scaling. This is how you solve the problem, right? So we just copy pasted this entire thing and copy paste, and instead of having this RAM, we just made the RAM bigger. Right. What could go wrong on day two?
You can't add a much bigger RAM.
So you again ran out of RAM. So are you only running out of RAM?
It's also it could be a single point of failure. Like if that machine crashes, then for that time you have downtime.
Correct. So day two could be when you're getting too much of request, your machine is becoming a bottleneck, right? And let's say you'd want to like the number of requests. So your RAM is still okay, but the number of requests that you are getting is way too much, right? So for your one machine to handle, right? So let's say you'd want to have too many requests, but RAM is okay. Now what would you do?
Increase the number of API servers.
Okay. Let me do this copy paste. So how would we increase our API servers? So ये एक API server हुआ. Now what?
Add a load balancer before API server, and we can have multiple API servers, which might be in round robin, and a centralized cache for all the systems, all the
Okay.
API servers.
तो ये तो हटा देता हूँ मैं, ठीक है. So the first thing that you'll interact with is a load balancer. Then it would be some API server, and then you added one more API server here. Right. Now, with the first one that we have, each machine would have its own RAM. Right. But this would have a problem, right? Because now instead of having one RAM, you are having, or one storage node, you are having two storage nodes, because basically depending on where the request is going, it would, matlab, your data might exist and might not exist. So your load balancer. So here you're directly started making your cache. You have already started making your cache distributed, like basically sharded per se. So you are having two separate storage nodes. So better way to, so, but if the RAM is not the problem and only API servers, which means we need a common RAM. So how would that problem be solved?
Yeah, maybe host add a data machine which the API servers interact with.
And there you will add a RAM.
Yeah.
Something like this. So let's call this thing storage node. Did everyone understand why did we have to do this? No? Because RAM was sufficient. If we just replicated the part where your hash map, see, the implementation that we went with was like we store everything in a hash map, and this hash map was part of the API server. Now, when my API server started getting a lot more requests, it ran out of RAM eventually. So then we scaled up. So I still have one API server, one gigantic RAM. But now when I'm getting too many requests, my RAM is doing well, but my API servers, the number of requests that I got was too much. So I need multiple API servers. So either too many requests or want to avoid single point of failure, any of those. So I'm adding a load balancer and two API servers, but I can't have my same code running, which ran on day zero, because on day zero, my hash map was part of my API server. So if I do that, I would be having two sets of hash maps, like each one residing in one API server. And depending on where the request is going, my key would either be present or absent, and I'm directly making started cache distributed. But if you see, when you are splitting this thing, it's not about like we don't want to make it distributed, but if you see, RAM is very costly. Let's say each machine was like 128 GB big. So if you are doing twice, if you are adding 2 times the machine, you are literally doubling the cost of your service. And so thinking about that, you would want to have one machine that is having gigantic RAM, and you can have very cheap API servers, right? Because API servers is just like getting the request and just basically going to the storage node and getting it. So that is where, what did we do? We took out the storage part of it and created a separate machine out of it. So even the storage node will also be a normal server, a normal API server, but this API, a normal server who understands HTTP request. The request from client will go to API server. API server will internally talk to your storage node in any protocol. It could be HTTP protocol, it could be normal TCP connection, it could be UDP if needed, it could be anything, or a normal TCP connection over raw socket. HTTP, anything that it would like. But then the storage would be present in just one place, like because RAM was okay. So this RAM is, let's say, 128 GB big, and it is here. So API servers cheap, they all communicate to this server and they talk to, and basically they all talk to the storage node, which has a nice big of a RAM. It gets the data and it sends back to the client. Right now, when we talk about it, now that our evolution reached this point, now something fancy would happen where my RAM, after even doing vertical scaling, after even like 128 GB RAM, it wants more in-memory resources, right? This is where our problem of distributed cache would come in. Unless and until you reach this point, there is no point creating a distributed cache, right? Your system in general has to evolve through day 0, day 1, day 2, and then you'll move to the third part where now I definitely need a distributed cache. Yeah, Ronak?
Arpit, like in this, like in the first category, we told that since our RAM we are increased. Now what we are doing is like if we are getting too many requests, we are increasing the API server. So but in the day two final design, in the end, like we are having the same problem, right? In storage, like in storage one node, there will be too many requests in the API server. So we are going back to again to the first problem that we had.
No. But with the storage node, see the time it takes for you to respond back. Right. For example, let's say it's a great point, by the way, when the number of TCP connections that you are getting, maybe your API server is doing a few more extra things, while your storage node could be big enough to handle as many TCP connections as it needs. Right. So now what could happen is your you can have as many, you can potentially have 1 million TCP connections handled on one machine, right? But would you want to have all of those connections as part of an API server? Matlab, your API server, or rather, would you want an API server to be that big to handle so each of an API server to handle those many TCP connections, right? So you can have a cheaper API servers because you'd want to avoid single point of failures.
But here also we have single point of failure, and like to be honest, like Arpit, in storage node also we are handling 1 million requests or something. So if we like, and if we are bombarding it with 2 APIs, and 2 APIs will throw 1 lakh or 1 lakh like at peak, let's say. But initially, if we even scale the API server, it wouldn't matter, right?
But then the request, but then there would be connection pooling, na? There would be connection pooling. The TCP connections could be reused. The number of requests. So unless that becomes the bottleneck, right? So the number of requests that you are getting to a storage node would always be equal to the number of requests which is being fired by the user, right? But the way the connection request would be handled would be very different, because here you would have a connection pool on your storage node and on your API servers. So there would be like a fixed set of TCP connections over which the communication is happening between the two, right? But when you cross that thing, so that is when your storage node is getting much bigger or large number of requests to be handled, which it is unable to handle. So your data storage, we have separated out here, making basically avoiding single point of failure in API server.
Right. One more thing, Arpit, is this, like if we cache little bit in API server, then it can be like, it will be more useful, right? Because you don't need to go to storage, then like then that
What
way.
will you cache there? Acha, you mean to say any response that you get from storage node? Yeah, वो तो सब कर सकते ना, वो तो सब obviously कर सकते.
That would help in this design, right?
Yeah. You can anyway do all sorts of fancy stuff, that you can cache data on API servers. You can cache some response on client if needed. You can do a lot of fancy stuff there. So that is all there that we discussed in the past thing. That is all here. That all is applicable.
Okay.
Yeah, Vishal?
So my question is also again the same points. So connection pooling, if we do, right, but if there are requests concurrent, right, then we are adding delays, right, to the system. So I mean, then the point of,
but then if you don't do it, then how are you avoiding single point of failure?
No, here I'm actually not understanding how we are exactly avoiding single point of failure. because
Your
the
API
storage
servers might
node.
break, na? Your API servers might break. If you are just having
Yeah.
one API server whose job is to handle all the, whose job is to take in all the requests, also act as a cache, all of those things, right? You would need multiple nodes. Like, see, how many requests? So how will you scale your API servers? You would be vertically scaling it up,
Yeah, that's correct.
right? When you're vertically scaling up your API servers, so your API servers, when your API server receives a TCP connection from your client, right? Every time a new TCP connection is created with the client, now this API server handles the TCP connection, plus it also holds the cache data, right? This massive cache data. Now now basically with this architecture, what could go wrong? Your API server might die off.
Yeah.
Right? And if your API server, and why API server is much more vulnerable, because the request that it gets from the client will in most of the cases, every time it might create a new connection. That's the worst case, that every time it is creating a new connection with it. So the file IOs that would happen, because in Unix everything is a file, the file IOs that would happen is costly. Secondly, the API servers are not linear. Now, my single point of failure API servers my problem would be that ठीक है चलो मतलब I can talk about it, but if चलो let's say I'd say that this is not really a good solution, because I might just ramble a few things, but that might not really add up, because like you can still have it. Okay, so then would you say that day two architecture there are a lot of problems? Like why would we need to do this?
Yeah, I mean, point is why, I mean, we are adding load balancer to API servers, and then again we are routing back to the same old problem. वो वहाँ पे थोड़ा I'm not clear.
What's the old problem that you're talking about?
Old problem में we API server was a single point of contact, right? Single failure of contact, right? And here storage node is a single failure of contact, right?
हाँ तो उसको
Single
split
point of.
करेंगे ना, उसको करेंगे ना split.
Okay.
But then obviously my justification of this was like I would want to have a central storage system where my cache data resides, number one. Number two, what I would want is my API servers to be very lean so that I can scale up and scale down. If I club both of these but if I club these two things together, my storage node and my API server has to scale together. Right?
Yeah,
because
so
my
obviously
RAM,
you would add some more capacity, some
exactly.
more
So,
redundant.
basically, I might not be able to split my API servers into two, making API servers a single point of failure. So by first splitting out my storage node, the main reason why I did this was I want to have a central storage place which acts as my central cache, whose job is to just store the data, right, and not worry about anything else, so that I can scale up and scale down my API servers at will. If I'm not doing that, I'm constantly having machines that are running, number one, plus they would be handling connections and doing a lot of stuff. And so what I typically observed was like when we have storage and API servers together and we try to scale them up and down at the same point of time, because like let's say if I'm getting enough traffic and I'm just scaling up the servers, with respect to cost, it was a major impact, but okay, let's not bring cost into this picture. But having a central place for all the for all of the storage node made a lot of sense. And for single point of failure of storage node is something that we would obviously have to get rid of. So obviously it would not be just one machine that would be there. The data would still reside in that one machine, but a copy of the data would be present on another machine. Maybe a cold standby sort of stuff if it is that critical.
Okay. No, it's fine. I mean, I understand. We'll definitely add.
Obviously, it is better. But I 100% get your point. The justification which I gave might not be that sensible enough, but it's just about having that clear separation of responsibility. My API servers are scaled separately. My storage node is scaled separately. API servers per single point of failure doesn't happen. Storage node right now is suffering from that, but it can be rectified later.
Great, yeah. Let's move on.
Sure. Yeah, Anshuman?
Yeah, so I'm thinking that there will be network IO, right? now to storage server
Yes.
from API servers. So
Yes.
that is one thing that wasn't happening on day one design.
Yeah, but that is anyway, malab, you would have to have something like that happening where where someone is talking to your storage node to get the data. It might make things a little slower, but at some point you would have to do it. If we don't talk about cache, and let's say our storage node was a normal database, would you have accepted the design?
Say again, if it was a normal database.
If it yes, if it was a persistent database.
Okay.
Just imagine this is S3, right? So
Okay.
there might be API servers of S3 who are handling a request. There might be a separate service whose job is to just store the data in disk, right? Would you want all of your API servers and your storage node to be clubbed together? Matlab, the storage and your API servers to be there in that one place, in that one machine, right? Because
Yeah,
what if that
I
machine goes
wouldn't.
down, right?
Yeah.
Right. So let's say
So one thing that I got is we are separating this only because API servers are cheap and scaling them up is cheap. And then now we can
I'm
see how.
basically making this fault tolerant. So that's a good way to put it. I'm just making it fault tolerant. So
Okay.
because now what would happen is if I have my API servers and my storage node together in one machine, and if that machine goes down, right, that becomes a problem. Correct?
Correct.
Right. And this is much clear when we talk about S3 or when we talk about a normal database, because if I have my database and my API server on that one machine, and that machine goes on, it takes everybody with it. So I'm just splitting those things into two different points. I can scale up. So basically scaling up API servers could be a byproduct of it. So I can scale this thing basically using cheap machines to run my API servers, and I can scale this up and down as I want. And I can then just worry about how would I make my storage much more fault tolerant.
Correct. Separate them and individually make them fault tolerant.
And individually make them fault tolerant.
Okay.
Okay. This would make a lot of sense. Okay. Thanks. Yeah, Prabhat, final question before you move on.
Arpit, like, can we also do like request collapsing on the API server? So for example, like if
sorry, I'm not sure what is request collapsing.
So for example, like if we have like 10 requests coming from 10 different users, and like say like those 10 different users have some common key values pairs that they are accessing from the storage node. So like I've seen
basically batching it in one place and then basically not doing repetitive work.
Yeah, so I have seen this feature in CDN. Like if like through this feature, like we will reduce the overall request that the storage node
can do that. You can obviously you can do that on API server. You can make API server as smart as you would want. Like let's say if you just have two API servers and all the requests, like let's say all the requests of a certain key always goes to one API server, then you can very well do that. You can actually cache the thing on API servers. Okay. Right. Chala. So this is a good enough. And now once we hit that, obviously now this makes much more sense. We have made independent, basically individually fault tolerant. So worrying about storage node separately, worrying about API server separately. Now we come into like the core design of it, like our cache API server. So we run. So in general, this is the most common question asked to me, like how would our cache server actually look like? So your cache is nothing but a very simple web server talking HTTP that understands commands like get, put, delete. If you are implementing Redis, it's a normal raw TCP connection that you create with Redis, on which you send commands as a certain protocol, where the first 3 bytes would be this, the next 5 bytes would be this, and so on and so forth. You make calls like this, you get response back, and you then do the needful job. So these key value stores, as we all discussed, like these are stored in hash tables, Python dictionary, JavaScript objects, or anything similar, key and value. It is as simple of a storage as this. But then the next thing with what we definitely have to worry about. So that was a very nice high level stuff that we saw. How would we split the things? But there is another thing, like in most cases, what we do, or in most cases, cache are bounded. So your machine, like here when we talked about the RAM and then we increased it, obviously RAM has a limitation. Let's say 128 GB RAM. That's a massive machine that we are working on. So the cache gets full. So you would always allocate a fixed amount of memory to your cache process. Basically your storage node. There would be like a fixed set of memory. It won't be storing it. But then it has to understand, or your cache storage node would have to understand that, okay, I'm hitting that limit. Now what I want to do is I want to evict. So when your cache gets full, to make a place for the newer entry which is eligible to be put into the cache, the old one needs to be removed, which is typically cache eviction. So there are tons of algorithms which you can implement here. So algorithms like LRU, least recently used, in which the oldest entry of the cache is removed. A great use case of this is, first of all, CDN, obviously LRU, because the newer data is something that is very highly accessible. But a great example of this is news. So if you are building Google News or something, how likely are you to access news of a week back? Not much, right? So the algorithm that works very well, or the cache eviction algorithm that works very well for evicting entries in case of Google News or something similar, is like LRU algorithm. So least recently used, you would be evicting it. Another good algorithm is LFU, which is like least frequently used, or the entry which is used least frequently is removed. A great example of this would be Wikipedia, right? So an infrequently accessed data which is least likely to be used. So just think about like popular pages on Wikipedia and unpopular pages on Wikipedia. So unpopular pages might just like once a while someone goes to that pages and read the stuff. But the popular pages, even though the popular pages, so a very strong case here is, let's say a page like Sachin Tendulkar page. Okay, that page is not opened a lot for like, let's say 2 to 3 days, but it was a popular page. Right, given that sort of situation where there might come a lean patch for a popular page to be not accessed at all, but I would still want to keep it in cache because it was very frequently used. Right. So this is a very good example where you would want to use an algorithm like LFU, not really being biased on the recency, because that's what LRU is biased on. That if it is recently used, I would keep it in the cache. But with frequency, it is like if this was frequent enough that there might come a lean patch where someone is not accessing it enough, I would still want to keep it in cache because it was a very popular page. Right. While the unpopular pages, I might choose to, use it. I might choose not to cache it because just like it is like just once a while access, it might be some outlier. People are just accessing this one page like one odd time. Right. So these are the cases where, LRU and LFU, like you can pick one over the other. Right. And then there comes a very random algorithm called random eviction. This works very well. We tried changing this algorithm for a certain use case. Although, to be really honest, random cache eviction algorithm actually gives an equivalent performance as LFU and LRU. So in most cases, real world way, there is no big of a, so no, not especially in case of CDA, but for normal, like our access pattern of a system, like we did this at Practo, where we served a listing of the doctors and search results and hospitals and whatnot. And then we just tried to do it like one day we just saw ki chalo, let's try this up, a random action algorithm. Why? Because it has a very less memory footprint. If you see the way the amount of memory you would need to maintain LRU and LFU, like all those of linkages and structures like linked list and priority queue and whatnot, versus random eviction does not really require anything. It just picks one at random and evicts it. Right? It worked really well with a very low footprint. The reason it worked well, this is like we were also shocked. Like what if it would have deleted something like the most popular hospital or the most popular doctor, like people are hitting it, and then I would have to again go to the database. The reason it worked well was because 85% of our data was cached. If you are very heavily caching the data, then you can actually use random eviction algorithm, because there you can add more data to your cache and your cache misses are very less because 80% of data is served from the cache. So this was a great insight which we got. So if you are into this microservice architecture where your microservice has a very limited data, let's say the microservice that you are handling has a total of 16 GB of data. And what if you use 12 GB of cache? Right. So typically almost 100% of your data is lying in the cache. Right. So you can use random eviction algorithm because in most cases, eviction is not even happening because your cache is not even getting full. Right. When we drill down, since we were really shocked to see the performance, when we drill down, we realized that we did not have a lot of cache misses. So because of which like everything was served from the cache and similar performance which we got. And then we explicitly ran a load test around like judging by different frequency pattern or sorry, a different access pattern. And we did so random eviction did randomly evict the page which I was about to access, but had a very minor impact on it. But when your system is very heavily cached, you can, nichol all the performance out of it by just switching the algorithm to random eviction and not invest into data structure that powers LFU and LRU. So one thing that you should definitely do is read about implementation of LFU. So basically LRU implementation is fairly simple, it's fairly common, but LFU with order 1 complexities. So LRU can be done in order 1. LFU people think cannot be done in order 1, but yeah, there is a paper which I found which implements LFU in order 1 as well. Obviously, when you go through now, and I have anyway written an article on that, LFU in order 1. So when you are reading that, you would understand the kind of additional data structures that it requires for it to implement, right? And basically that is where you would see that it's not the memory of the data. Like let's say you are just caching integers to like 4 characters string or something, or like a cache value is very small, right? Then the most of your memory is being consumed for managing this expensive data structure that powers LFU and LRU. Right. So obviously to gain a good time complexity, you would have to give up on space. So you would be consuming a lot of space. And that's what exactly happened when you try to do LFU in order 1. So just go through the implementation of LRU and LFU in order 1 to understand what kind of additional pain points that would come in. Right. So understand the data structures, time complexity, and space complexity of it. Okay. The third most important part of any cache would be like TTL, something that we have discussed a lot. So each storage node or your cache storage node would need to have a process running or a thread or something similar that would go ahead and delete the expired entries. So similar to how we discussed expiration before, and we'll do exactly the same. So input we would obviously ask how long do you want to keep the key in memory? But while storing the data, while we'll store the expiration, what we'll do is we'll store the absolute value. Let's say 157230067 is my current epoch. And then I say that after 100 seconds, I want to delete the key. So you would actually store 157231167, right? So through this, we'd be able to efficiently delete the data. What kind of data, one question, what kind of data structure would you use to implement efficient expiration? How would you find the keys that needs to be deleted?
Heap is a good one. I mean, you can actually get the latest min or max based on your storage. You just pick the latest one and delete.
Pick the latest one and delete. So mean heap, max heap?
Yeah, min heap will be the right one.
Right. So the great advantage of storing the actual time is, again, you would have like, okay, so basically the only constraint that we have here is we can use heap data structure, but the only feature that we actually need is any data structure that would help us keep the keys sorted by expiration time in ascending order. As simple as that. So long as we have a data structure that would efficiently give us or that can efficiently keep my keys sorted by time, that is something that I would want to implement it. Mean heap is a great example. I've heard that there are a couple of other data sources that do it. I actually forgot the name. I'll basically look up and share. So there are a couple other data structures that would do a good job, because with heap, you know, the advent of, or the extra cost of rebalancing comes in. So there are other data structures where you don't really need to rebalance the stuff a lot. But yeah, so there are some caches that use that. So anything that would keep your keys sorted with respect to expiration time is something that you would need. So this is very similar to garbage collection. It identifies the item that needs to be cleaned up and then it deletes it. So priority queue is a great example, or heap. And usme the priority set as absolute time of expiration, like 15723 So it will be sorted by that. The top of the heap is the key that is eligible or that could be removed. You'll just check if my current timestamp is more than the key, I would be deleting it. Right. And along with this, you'd also have a check on your get or on your get call, where let's say your job runs every 5 minutes. If your key is not deleted within that, your key is still there and your user is accessing an expired key. So better way to also do it is always check the data while you are returning if it is expired or not. And because anyway, eventually the job would kick in and it would delete the data. Okay, priority queue where priority set to this, implemented using min heap. Item to be deleted will always sit at the top of it. Okay. So something that we discussed, a single node. Yeah, Varun?
Yeah, I mean, I want to discuss about the randomization that you.
Please.
Yeah. So when you said that you got more performance, same performance, basically, I mean, I doubt what is the memory consumption. I mean, you are using the same memory
100.
level.
See what happened exactly. So our primary data store was, so although our database was around 100 GB provision, the total data size consumed was only 16 GB.
Okay.
And the cache we had was 12 GB.
Okay.
So it was like almost 80 to 90% of our data was stored in cache.
Okay. So I mean, what I was comparing is the cache that is using earlier. I mean, so previously, let's say you are using LFU and it's provisioned with the 12 GB RAM, and the same cache is provisioned with a random eviction policy with 12 GB RAM. So it might have cached more compared to the previous one.
Exactly. Well. So basically, random eviction cached more data. So our total size was our total data was 16 GB. The cache size was 12 GB, but the amount of data that was put in due to random eviction, because it did not really require to manage data vectors, was a little extra. But we actually couldn't find a way to do it. We just went through the keys count that was there at peak time. We found that the keys were approximately 5% more, 5 to 6% more. Okay. So we had about 3 million odd keys or something. So the number of keys that was stored during peak hours was a little higher for random eviction. And then once we saw the difference, because we were like really shocked, how come the performance is equal, basically nearly equal. And then while we were going through metrics, we went through the number of keys at every time. And then we realized that the number of keys that was stored with random eviction was a little extra as compared to LFU. And then we drilled down why was it? And then it turns out the cache does not store, or it does not have a hard limit on the number of keys. Obviously it won't. It has to put a limit on the data that it is actually storing. So it has a massive allocated heap. So on my cache, there's a massive allocated heap, and then it computes the size of the data which is being entered. So it typically uses the size of the C Vala function that it has to basically judge what's the size of the data that I'm storing here. So it uses size of to measure, and then it basically says, okay, now my cache is 80% full, 70% full, and at that point of time we see how many keys exist in the cache.
Yeah, really, I think it's very great that you have seen the number of key metric and realized this. Yeah.
See, so I definitely won't recommend using random eviction out of random, but but in most cases, if you see, because there are because once you split into microservices, the amount of data you are handling becomes too small, and once that data becomes basically as compared to the overall data that your company might be having, if the data is too small and you can bear a cache ka load, you can get a you can actually get a great performance out of random addiction.
Yeah.
That's a great. Matlab, that was something that we did out of the blue. Matlab, we just read somewhere ki, Redis. We were Memcache. We used Memcache at that time. So Memcache, but there was a setting where we changed it to Redis. Oh, sorry. We basically changed it to random, and then we tried it out, and then same performance. Like, okay. Yeah, Rahul.
Regarding deleting the cache, why can't we do in a batch instead of doing it single?
No, you can do it in batch. Matlab, unless and until your top becomes or the expiration time of the element sitting at the top of the cache is more than sorry, if it is less than my if it is more than my current epoch, then I would not be deleting it. So till that point, I'd be pulling one out from the heap and then deleting it. Matlab, basically batching maybe you can do it once a while. Matlab, it's not that every time or your job runs on every GET request. It would be run it would be run periodically. Let's say once every 5 minutes.
So because rebalancing the heap will take length of the tree.
And basically this is exactly why. And by the way, how would you do batching in priority queue deletion? There is no winner.
Yeah, but we can access more than one element at the same time. Like
in priority queue?
No, I mean you can iterate through the list queue.
So I've seen one
multiply
implementation that implements this as a linked list. So what they go for is again a great optimization. I just read it somewhere. I've not tried it myself, but I've read it somewhere that someone tuned Redis to store it as a linked list. So it was a long back in 2015, 2016. Someone actually cloned the code base and then they changed the algorithm to use a linked list for their use case. Through this, what they did was they wanted exactly, so they had a very high, so every single key that they added to Redis was having an expiration time, but this expiration time always moves forward, right? So they were having fixed expiration time for all the keys that are inserted. And this was like flat 10 minutes or something. This was flat across any IO operation that happens on Redis. So through this, what happens is the time always, or the expiration time always moves forward, right? Since it was uniform across all the keys, so they wanted to leverage this. So they stored this in linked list. So now with this, what happens is every single key inserted is typically an append operation, right? Even in this list of expiration time. Correct, because since my time is always moving forward, so my expiration time is always moving forward, and it is directly proportional to my current epoch. So both are moving forward at the same time. So all the things were like basically pushing it at the back of the linked list. So it was just that. And then while deletion, they just went through the linked list and they just deleted in batch. Something very
can find more of cache misses. It's like once it all get deleted, then we have to repopulate everything, right? So that there'll be a lot of cache misses.
So but then the time was, so the expiration time was not constant, but it was flat. So like expiration time for every key was basically 10 minutes, depending on when it is inserted. I was talking about that, not that every key was expiring at the same time.
Okay.
Right. So this means that when time is moving forward, let's say t equal to 0, I'm inserting one key, it would be expired at t equal to 10, right? And then at 1, I'm making 1. So then the second expression would be 11. Right, something. So my expiration list, the way I'm inserting my keys in the cache and the time at which it would be expired, it was having a fixed window. So it was really easy for that to maintain this. So this was I read long time, I just recalled it. Like they did this, they used linked list to handle the deletion because they always were moving forward in time. So problem with that.
Yeah, actually, this is amazing. Like instead of maintaining a heap, you just maintain a linked list.
So linked list पे, so having a fixed concept, because this is also a great optimization. Like you कर सकते हो, मतलब why not? And you would get a great benefit out of it. So now you can delete in batches because you just go through the linked list, find a point where it breaks, and then you delete. And basically, while doing that, you are then basically invoking DLOG every. And obviously rebalancing the cost is also safe because now insertion is typically an insertion at the back end of the list, which is order one operation. So many fancy optimizations out there. Now, basically, this is exactly why I love reading research papers, because this kind of stuff is only found in research papers. So even that guy, the implementation was, he took an inspiration from the research paper and then he pointed it out, and then I went and read the research paper of that. So single node architecture. So with single node architecture, what would have something that we discussed, limitation like your memory would go up, connections would be there, solutions would be like vertical scaling, when you have a lot of network connections, you can. Why did I put this thing? Okay, when you have a lot of network connections, you would typically scale up vertically to a certain limit, but then like after a certain stage, you might choose to go horizontal. So typically both solutions could be applied when you are having a lot of network connections coming your way. API signature, fairly simple. Get HTTP get on key 1, you give K1, and then in the body you pass V1, and delete me, you'll give K1. With a get, you will have an optional expiration time. When doing that, you check the hash table. If the key exists, you would get the value and then return it. Put would be updating the hash table, deleting would be deleting the hash table. So scaling, when with a single node architecture, you would always do vertical scaling. After a certain time, you would have to move to horizontal. Chala. Now the most interesting part, concurrency. So Varun said that we'll use hash map, but if you want to deal with concurrency, we'll use concurrent hash maps. Okay. But how do we handle concurrency? So let's say we only add hash maps, but how would we in general handle concurrency in the cache? Where would we need it, and how would we handle it?
Locks.
That's a solution, but where would we need concurrency? Why would we need concurrency?
Let's say if I'm putting a key value, or I mean, I'm reading a key value, but you are trying to delete it. So that, I mean, that's the location where there is a conflict. Read, write, different operations.
Okay. Would there be any problem if you read something that is about to be written? What kind of problem would you fall into with caching?
Tail data. I mean, the one you said, right?
But with caching, it's still okay because is cache. Huh.
I mean, basically concurrencies happen when two writes are happening, right? On the same key. So I don't want that, right? I want them to be atomic. So that is one place.
Nice. Thanks a lot, Anjuman. Good points. So more than this is a major concern. How many of you agree on this? Reading while write is happening, or basically reading stale data, is less of a problem as compared to two writes needing to be atomic for cache. Or rather, how many of you disagree to this?
Arpit, in this, you are writing concurrently, right? So concurrently will be a switching of process, not parallelly, right?
Switching of process?
Like, let's say
concurrency and parallelism, basically even parallelism is concurrent, but the way the people are using concurrency is a little wrong, because they both actually basically concurrent and parallelism in this case are synonyms. So it's two threads which are concurrently being scheduled on two different cores running in parallel, trying to make writes.
Right. In this case, it is same. Yeah.
Is
the only case against is maybe for like a purge like use case. And if you have a large TTL, then that specific case, your data can be stale for a long time. Like CDNs, like if it's on the order of days or hours, then you don't want to that may be a problem in such cases. Otherwise,
right? Because in most cases, so this is exactly why we should always understand the use cases our caches are serving, right? Matlab, we blindly use cache to like cache the things, like, but to get a really good performance out of it, like you should have to understand how it is, like something similar that we discussed with the linked list wala approach. This is also very similar to that. Like people typically say reading when a data is being written, because that's the first thing that comes to our mind, that okay, I'll read logs for that because I would not want to read stale data. But in most cases, like 99% of the cases, caches are being used to, they serve the stale data. And when you're reading it from the cache, you are always ready. You are always prepared that the data you might be receiving would be stale, right? So in some cases where you're using cache as your source of truth, right, that is where this might create a problem, where, reading stale data might not be acceptable, but using cache as a source of truth. Acha, by the way, any example where we use cache as a source of truth? Ek example de do bas. We have seen this already. Come on, guys. Cache as a source of truth. One example.
When we were scaling WebSockets, we were storing.
That could be one, yes. But wahan pe it was basically pops up. So that is still okay. That was pops up. You saw this, guys. Karo, yaar karo. Remote locks.
Yeah.
Right? Remote locks, locking, where we use locks, where we put it on Redis. That is a source of truth. We don't have lock stored any other place. It's there only in Redis. Now, what would happen? Because there, that is my source of truth. So if my lock is being removed while I'm reading it, and if I read stale data, that would be a problem. That might incur a deadlock. Correct? Think so. Everything is covered, right? So it's just about like just having a very high recall rate here. That's it. So this could be a problem where source of truth. Otherwise, in most cases, serving stale data is okay. So this is where handling concurrency is more important, where when you are having two writes, which needs to be done atomically. So let's say two threads coming in, and the threads coming in is both are doing a, one is doing a equal to 10, second is doing a equal to 20. Right? This is where we would have to handle, or we would definitely need to have atomicity. Right, where we definitely need to make these things atomic, where where only one, where basically these could be like 100% serializable, where first a equal to 10 happens and then a equal to 20 happens, or first a equal to 20 happens, then a equal to 10 happens. Right, so depending on, it should be serializable, it should be ordered, like it should not come into a state where you don't know what the final value is going to be. Right, so this is where you definitely need to have two writes needing to be atomic, and concurrency needs to be handled. Now coming to the solution, Varun said locks is the solution, but any other solution?
Single threaded.
Best. Loved it. Make it single threaded. Bread. I'm बिल्कुल नहीं सोचा था, और जबरदस्त आंसर है. Make it single threaded. मतलब did everyone understand why making it single threaded would solve the problem? मतलब कुछ parallel में चलेगा ही नहीं तो कहाँ ही फटेगा कुछ, right? So make it single threaded, and which is and this is something that is leveraged by Python a lot. Python is a single threaded process, right? So Python, everything is single threaded. So due to GL, so the way they avoided handling atomicity or like multiple threads, because it is single thread, एक time पे एक ही चलेगा, no two things in parallel. Yeah, Anshuman?
Yeah, a single thread as in Node.js. Just
Node.js,
one.
exactly. Basic Python,
Okay.
Node.js, all of these are single-threaded one. So
Okay, yeah.
let's
So
not
these
even have let's not even have parallelism in the system. मतलब ना बजेगा बास ना रहेगा बास ना बजेगी बांसुरी. Right? That kind of situation. Okay. How many kind of lockings? How many kind of locks have you heard of, or locking techniques?
optimistic, pessimistic.
Optimistic, pessimistic, right? Okay. And is
Mutexes.
there a third one? I'm just aware of two. Is there?
I mean, I'm not. No, I don't.
Right. So why I'm writing optimistic and pessimistic as two? I'll come to it. Optimistic locking. We will use this thing a lot in the coming sessions, like optimistic locking, pessimistic. This is extremely critical. Okay. What are the advantages of one over other? So see, hands down, single threaded wins the battle. Matlab khatam. Matlab make it कोई problem नहीं. But with respect to locking, we typically see locking as a great solution whenever we would want to make something atomic, or let just one happen, or like happens in a serialized way. So where would you pick optimistic locking and where would you pick pessimistic locking? Or in general, what are advantages and disadvantages of it?
Yeah. I mean, if the possibility of conflicts is less, then it's better to choose optimistic locking. If the possibility of conflicts is more, then choose pessimistic lock.
In a read heavy system, we might prefer optimistic locking.
So what is cache? What is cache? Is it read heavy or write heavy?
Read heavy.
In most cases, it is read heavy, but again, it would depend on your use case. 99.99% times, cache is a read heavy system, unless where we use cache as our source of truth, where it becomes write heavy, especially locking, right? So you need to understand where are you having a system which is read heavy or write heavy, and then you'd pick one locking over other. So as very well put by Varun, optimistic locking is where we are being optimistic that there would not be conflict. But if there is conflict, we are still prepared. That's what optimistic locking is. Pessimistic locking is by I am pessimistic. I would only proceed if I have lock. Otherwise, I would not going to proceed. So typically the mutexes and the semaphores that we saw during operating system classes, and that's where that's a classic example of pessimistic locking. I'll just make it. So that's a classic example of pessimistic locking, where your process waits until it acquires the lock and then it moves to the critical section. Here the critical section is updating the value. So unless and until I have the lock for this key, I'm not going to update it. That's pessimistic locking. Optimistic locking says key, it's okay. If I'm having very less chance of having a conflict, I'll still go through, but I will do retry. Right. So we'll see how both of them are implemented, and it's a great way to get performance out of a system. So because if you see with pessimistic locking, unless it has lock, it would not move forward, which means it would be blocked until it acquires the lock. So it would basically slow down the entire. So it would basically slow down your entire system and basically hamper your throughput. With optimistic locking, it would not worry about it. If there is a conflict, it will automatically retry. That's what optimistic locking is all about. So this is where the part is. So once we complete conference, we'll go on. बाद में आगे बहुत interesting चीजें cover करते हैं, ठीक है? So with respect to get keys and all, it's okay. It need not be you need not be handling concurrency because everything is get and sub get ही हो रहा है, so that's okay. But when two or more puts or delete requests come to our cache at the exact same time, this is where the classical concurrency problem comes into the picture. So in general, the rule of concurrency says that you update what you read, which means that if you are updating something that you have not read, because basically what this implies is if you are updating something that you have not read, which means that after you read, if someone came in between and updated the value, you are not allowed to continue with the write, or your write should fail. This is where the conflict comes in, right? So this is what this is something that optimistic locking optimizes for, where it would check that when I'm updating something, it is still the same value as what I've read it before. I might have not covered it. I'm not sure. Did we cover optimistic locking with databases in past session? I kind of forgot. Did we cover
No,
it?
we did not.
We did not, no? ठीक है. I'll just spend some time. आगे है शायद से. I'll just spend time doing that. ठीक है. So with optimistic locking, the idea is very simple. So I'll just cover it now. Repeat हो गया तो अच्छी बात है, but miss नहीं होना चाहिए. ठीक है. So I'll just cover. So with pessimistic locking, what would happen is you would acquire a lock. You would acquire a lock, then you will act, and then you will release the lock. Right, and this act is nothing but update or delete or do something. So this becomes your critical section, right? So now this same piece of code, which is being run on all sorts of API servers and storage nodes, whatever you would have, every single thread would be waiting until it acquires a lock, and then it could go ahead and do the action. But with optimistic locking, this becomes very simple. What it does is, it would say, like, let's say you are implementing this on SQL side, because SQL query, everyone understands, it becomes easier for us to, explain the stuff as well. So the idea is, let's say my first transaction here was like doing a equal to 10 was the initial value. My update is a plus equal to 20. This is what I would want to do. So with pessimistic locking, I'll acquire a lock on a equal to 10, and then I'll make a plus equal to 20, and then I'll basically release the lock, or rather plus equal to a equal to 20. Okay. Now, if there were two processes who wanted to do this, let's say one was doing a equal to 20, another was doing a equal to 30. If it was pessimistic locking, the two threads that you'll be having, each one would come at a stage of like acquire lock. The one who gets a lock on key A would come here on the basically inside the critical section, which is where it would do a equal to 20 or a equal to 30. Let's say a equal to 20 got the lock. So a equal to 30 wala thread is still waiting for the lock to be acquired. Once the value is updated, then the lock would be released. Then my second thread would acquire the lock. So a equal to 30 wala lock will be acquired, then it would do the update, and then the lock will be released. Right. So one time, one thread goes into the critical section. But what optimistic locking says is, the code of optimistic locking would be with the same example, a equal to 10 equal to a equal to 30. The code that you will be writing would be looking something similar to this. I'm writing update a equal to 20. So my a equal to 20 wala thread would run this update a equal to 20, where a equal to 10. And my 30 wala thread would run update a equal to 30, where a equal to 10. Now, even though these two commands get fired exactly at the same time, right? What would happen? Only one of them would succeed. Correct? Because once one of the command gets executed, it would change the value of a to, let's say my first one ran. Let's say my a, let's say my first one came in, my first one ran first. It ran a equal to 20, where it updated a equal to 20, where a equal to 10. So my a's value got changed to 20. And then my second one ran. My second one ran would say like update a equal to 30, where a equal to 10. Right? But then a ka value is 20, so it would not match anything. So my update would fail. So this is a classical case of doing conditional puts. So conditional updates or conditional puts. So this is something that you should always be thinking about. Like optimistic locking is whenever you're doing conditional puts, is where you have basically kind of given up on like locking, doing pessimistic, like acquiring a lock and that, and then you would do a manual retry. So when your update is failed, you would do retry again, right? So obviously it depends on your business logic. So in some cases, you might do a retry to just see if you are succeeded or not. let's say if your update was like doing a plus plus, right? So update a equal to a plus 1 where a equal to 10, and update a equal to a plus 1 where a equal to 10. So in both cases, if this is the exact same thing, that fired, right? So depending on, like, you update what you read, because now if someone came in between and updated the value, it's something that you read a value, but someone else made an update in between, and then you are writing. So you might be overwriting the changes made by the other transaction. This is something that we would have to protect. So 2 ways to protect: pessimistic locking, you acquire the lock, do the update, return, and optimistic locking, where you do this conditional updates or conditional deletes or conditional puts. Okay. Yeah, Anshuman?
Yeah, can both fail?
If basically someone changed A to some other thing, then definitely yes. But yeah, if there are exactly just 2 things and the A's initial value is 10, then this will happen.
Yeah, okay. Yeah, so I was thinking that in this example itself, it can fail, right? So when A is checking for where A equals 10, and at that moment update A equals to 30 happened, then both will fail, right?
But typically that would happen in an isolated way. So you would have some sort of isolation, but yeah, that could be the case where the update would fail, and then depending on your way to handle the logic, it could depend. You would either retry or you would abort it.
Okay.
Yeah, Costo?
Hey, so this seems to be like very specifically used for database queries. So instead of like getting a lock on a row and doing this, we use this trick,
No,
right?
everywhere it
Yeah,
is there. So
optimistic locking, I mean. So like, are there like native C APIs where this kind of thing is used? Like, I don't understand that.
Compare and swap.
Okay. Yeah, but okay, yeah, perfect. Yeah, makes sense.
Correct. चलो वो भी लिख दो, भूल ना जाए अपन. Okay. So when you're doing compare and swap, and not basic compare and swap is an example of optimistic, a kind of example of optimistic locking, right? So yeah, so it's not just specific to it. So basically taking an example of database makes like simpler because everyone understands it. But there are thousands of ways to take example of optimistic locking, but database is the easiest one to take. That's why. But yeah, if for people who don't know compare and swap, look up on Wikipedia, read about it. It's a great optimization there. And basically we exactly did compare and swap through SQL queries here. Chalo. And yeah, before we go on a break, one thing I would definitely want you guys to check out is the kind of cache we designed till now. If you see, it just had get, put, and delete. If you see, you could have very easily implemented it using a normal database. You don't even need to have a standalone storage node and what else, all the stuff, right? Instead of having a in-memory hash map and whatnot. So what I would want is, can we, and if we can, how can we build this cache, this very get, put, delete with the same kind of throughput that we got with in-memory on top of MySQL database? Right. So my condition is we would want to have high throughput as similar to as like everything is being queried in memory. Right. So cache where we use MySQL as a storage node, but we get equal throughput as a normal cache we would get. Right. Because like already we have a database that could handle a lot of stuff. Like it has, you can do TTL handling, you can do concurrency, you can do every single thing that we discussed. So just replacing a self-written storage node by MySQL. How can we do that? If we can do that, then how? If not, then why not? Okay, do research about it. It would just take 5 minutes of Googling, but do that. I would want you guys to stumble upon a few really interesting things that you might not be aware of. So let's discuss this tomorrow first thing. Right? Yeah, Prabhat?
Arpit, in pessimistic locking, like while we have logged the A's value, like can we read at that time? Can I read?
It depends on the isolation level. If your cache would want to read uncommitted data, then you can do that. So you know there are different transaction isolation levels like read committed, read uncommitted, a serializable, like all of those things. So
a repeatable read.
It would basically jab repeatable read. So all of these things is something that would depend on your use case. So if your cache would allow that, you can do that. right? If you want to allow read, or you'd only want to allow read committed, so you can implement the logic in that way. Only the committed value will be returned, and so once the commit happens or once the update happens, so if you make everything atomic, right? So if every single of your update is an atomic operation, so then you are basically typically always doing read committed.
Yeah, but like then why do we have that preference when we have a read heavy load? We will use optimistic concurrency because like we can operate in pessimistic concurrency with a lower.
But if your write operations are atomic, so if your single operation is atomic, then you can always go for optimistic lock. Make sense? Let's say you are writing or you are updating something, right? Let's say you're putting a value in your cache. The way you have implemented your function is such that it is atomic in nature, using compare and swap, for example. If it is atomic in nature, which means even if you have two threads running parallelly, and still they won't interfere with each other. If your write function or if your put function is ensuring that, then you can get rid of pessimistic locking 100%. You can just rely on that write for, because every single operation is atomic. This is exactly what DynamoDB does, or even your Redis does. In Redis, every single command you fire, like get, put, delete, scan, or geo queries, everything, every single one command of Redis is run atomically, which means when you do two puts, even on the same key, would always, like, one command would execute, and then until that is being executed, nothing else would run. And the way it is implemented, it is not by taking locks, but by making it atomic. So if you're able to make every single of your operations atomic, you don't really need pessimistic locking at all, unless you're doing heavy transactions on that.
Okay, but like still like why it is better for like read heavy workloads?
Okay, when read heavy workloads are there, see, pessimistic locking way, when you're doing read heavy workloads, so read as in, so I'll give you an example on that. If the workload is read heavy, right? So there are cases when you let's say whenever you're reading a data from something, you're also taking a lock on that. For example, in SQL world, we saw, like, where we're taking shared lock or exclusive lock on rows, right? If you're doing something similar, if whenever someone is reading it, you are acquiring a lock. No one can update the data, correct? In some cases, you might also have no one can even read the data. Right? If you are having similar case, because you don't know how big of a transaction or how big of your operation it would be, right? So you would always be doing a generalization of it. So you'd be doing a read of it, basically read, and no one else can read it or update it. So then you are unnecessarily lowering the throughput of your system.
Okay, but like if we don't take that lock while reading, even if we are in pessimistic locks,
then
like,
it's okay now. Then it's okay. So again, it all depends on the low level implementation of it. So we can dive into a lot more detail about how can you actually implement it. But this is a very general use case. When you're having a read heavy system, right? Which means there will be a very fewer updates. So, and if you are operating at read committed kind of stuff, right? Which means that since there would be very few updates, so then locks learning ki zarurat nahi bachi. Right? So then you can directly serve it. So typically optimistic locking is, because since you're not doing a pessimistic locking key, not locking every time you're reading, that becomes a really pessimistic lock, like basically taking an exclusive lock at all the times.
Yeah, got it. Thanks. Thank you.
So again, it is very subjective. It depends on the, and basically that's what system design is all about. There is no one right answer. You can design the system however you want. It has to be optimized for the use case that you are building. Okay.
Yeah.
One final question before we go on the break. Yeah, Rahul.
Could you please explain the analogy for source of truth? You mentioned about the Redis cache.
आखिरी में एक बार cover करें at the end. तब लेते हैं. Okay. चलो. It's 5:25. Let's break till 5:30, and उसके बाद में we will cover. अभी तो बहुत बचा अपना, आधा भी नहीं हुआ. ठीक है. And then we'll cover horizontal scaling and then consistent hashing. And then one very and yet another homework basically think about a very interesting design that we will be covering tomorrow. Uska introduction. Okay, chalo, awesome. Uh, we'll meet up at 5:30 Wednesday. Sarthak, that's a great guess. So Sarthak basically guessed in the chat that can we use a large buffer pool? Great start, but there is something more that you can do there. Okay. Chala. So yeah, next part. How about horizontal scaling? So obviously when you're designing distributed caches, you are typically having multiple storage nodes. You would have a load balancer to balance the node. You'd have data which is partitioned, not shared. So basically without replication, and no basically set intersection is fine there. So you typically have this, right? And why am I introducing a very complicated architecture like this? Because this would lay the foundation of S3 design. It might not really work well for caches, but in general, this kind of architecture is very common when you're designing a storage engine. So basically, that is why I just said ki, well, even though we're talking about distributed cache, it could be like very well extended to any database. So basically, that's why I just wanted to cover this building block. Here, we can do something like this. Okay, so here what would happen is your user would be connected to load balancer, request would come to your API servers or your app servers. Then there is a load balancer which is load balancing across your storage nodes. So the storage nodes are the one that holds all the data. So the storage node 1, 2, 3, 4 are the ones that are holding the data, and then your app servers are flying in. So then you would typically, when you are sharding, in general, you would have a partition key. And depending on the partition key, you would apply a hash function, and then your data would reside on one or the other node. So let's say your key is hash to 0, the data would be stored in SN1. The key is hash to 2, it would be stored on SN3. Right. So, and all the operations that you see for the cache, get, put, delete, all of them are operations that happen on a key. And that's typically how your key would work. So NoSQL or a sharded sort of system is very easily buildable for a system like this. So the request flow that comes in would be like get a give me key K, the request goes to load balancer calculates I using fn of K mod n, like normal hash function that we have. The request is forwarded to the ith storage node, to be honest. And then storage node fulfills the request, generates the response, and the response is sent back to load balancer and then to the user. Right, a very very classical flow. So that's where a load balancer, instead of doing round robin or random or something, it has to work on this hash function. Like I would always, the load balancer has to be configured such a way that it is the request flows through that corresponding backends or your storage node only, right? But now there comes a very interesting architecture that I wanted to bring up. Is like, what if there is no load balancer? If you see like your load balancer, we are just adding one extra hop, right? So what if we do not have a load balancer? This is a very common architecture, by the way, where your request, so the load balancer which I removed was the load balancer that was between storage node and your app server. So that load balancer. So what if I don't have my load balancer there? So every single of your app server or every single of your API server would be connected to every single of your storage node, and the hashing logic or the hash function mod n wala logic would be written on all the four, or would be executing on all the 4 app servers. So it becomes the job of the API servers to have those text key. It would be, or ensure that they all adhere to the same hashing algorithm that is that everyone agreed upon. Ki f of n of k mod n wale index pe jaake it has to connect. So this is basically, there is a challenge there, which is what is solved using consistent hashing. But this is a kind of architecture that is very common, not just with respect to storage engine, but even when you are having to, or when you are sharding your data for the first time, you don't have a proxy layer sitting in between. Your API servers can create multiple connections to both the shards, and then have the sharding logic in the API server tuned in. Key, given the key, I'll find kahan pe bhejna hai, which connection should I send to, and then it sends or it fires a query on that particular connection. Something very similar. So this is architecture is not specific to storage engine, can be extended at a lot of places. But this is a classical mesh architecture where every single thing is connected to every other thing. And this kind of architecture is very, very common in real world. So you might stumble upon a ton of them, right? So when there is no cache, each server has to connect to every single of your storage node and perform the operation. So each server has to know about all the cache nodes so as to perform the operation, right? So obviously SN1, SN2, SN3, SN4, 4 storage nodes are there, 3 API servers are there. Each server would have to know where, or each server had to know at least 4 storage nodes are there, and in the order and all, like all of those things it becomes really important for all of them to know. So if you're scaling up at will or scaling down at will, this becomes a challenge. So how would you, but before we do that, now the thing at hand is, how will the application server know about my storage nodes like SN1, SN2, SN3, SN4, right? How would we design that? Because this is also a big challenge, because now what would happen is, since your hash function is let's say f of n mod k, f of n of k mod n is equal to I, index on which you would connect to. So here what is really important is understanding how many servers are there. So n, right? And even the order would matter, because the output of this would be I. So let's say in one of the API servers list, it is SN1, SN2, SN3, SN4. While on second one, it is SN2, SN1, SN3, SN4. This would become a problem, right? Because now for app server 1, a key should go into SN1, but that same key for app server 2, which is going to SN2. So this would become a problem, right? So the order in which you are getting is also important. The discovery of all the storage nodes is also very important. So how do we design this? So we would obviously have to have a common place. Obviously, whenever you see, so you'd see this as a pattern. Okay, whenever we are in a position to make arrangements like this, like I'd have to have very ambiguous information here and there. How am I tackling that? Right? How am I tackling a situation where I need just one source of truth? You just take the source of truth and put it at a common place. But typically a 3NF sort of stuff in our SQL world. Like, see, there is no data redundancy. Everyone goes to that same place to get that information from the source of truth. So this common location becomes our source of truth. It could be stored as a normal JSON file on S3. It could be stored on SQL database if needed. And in general, any storage system, like any storage system would work. So this is something that is very important. This would be acting as a source of truth for all the cache nodes that we have in the system. So what happens when a new cache node is added? This meta storage needs to be updated. When a cache node is removed, again, this meta storage needs to be updated. So now let's say I had 4 storage node and I had to scale up. I added a 5th storage node. Now when I do that, I'd be updating this common storage, this metadata store. When I'm updating this metadata store, what would happen? How would my API servers know about it, right? Because I've just updated the metadata store, but my API servers also needs to know. So this is typically implemented like either notifying the server through a persistent connection, approach 1, or a more common approach is that API servers once a while goes to this metadata server, gets the information and updates it locally. Like, because and every request it can't go to metadata server. So flow becomes like this, where you have your API server. API server is connected to your storage node, and there is this metadata information. Right, so API server and metadata information, basically every 1 minute, it would go and fetch the metadata information and hold that information locally. And then depending on that, it would be basically connecting to the corresponding storage node. Right, so once a while it would do a probing sort of stuff. It would probe the metadata server, get all the storage node, and then update it. But for that 1 minute, there will still be a hiccup. Right, this is something that would require addressing. So then another service that we would definitely require would be like monitoring service, because we saw that we scaled up, but what if one of the cache server goes down? So we need some service to monitor to configure the stuff. So it should monitor the health of the cache nodes. If any node becomes unhealthy, it's the responsibility of the service to update the metadata storage that we have with the node list. Array, this node went down, so now you can basically taking it out of the system so that no new request goes to that part. Or any addition of new node has to be informed to monitor service so that it can start pinging that server to check it, right? So you need another component in the system that would be monitoring. So it could the job of this service would be to ping all the configured storage nodes. Any new storage node that gets added, it adds it to the list, updates it into the metadata. So something like acting as a master or the puppeteer here. Like it becomes something that would actually keep an eye on all the nodes or all the storage nodes that I have to see ki array health full ori, health half ori. Now I'd want to do something about it. If the overall cache capacity goes up above a certain percent, notify a certain place. So you might want to have an alert or trigger service, something like that, which would do that job. So there's a distributed cache, looks easy, but it has a lot of moving parts here and there that needs to be implemented. Right. So a typical now would jump into consistent hashing. Right. The most common use case here. So let's say we have 6 keys, K1, K2, K3, K4, K5, K6, right? The hash value that we have, and let's say we just have 2 storage nodes, SN0 and SN1. So depending on the hash value, I would be sending my key to any of the storage node. So K1 ka hash value, let's say my hash function is fn some function modulus 2 because I have 2 storage nodes and I'll get the hash value out of it. So I say K1 ka hash is 0, so it goes to SN0. K2 ka hash is 0, it would go to SN0. K3 ka hash is 1, goes to SN1. K4 goes to SN1. K5 goes to SN1. K6 go to SN0. Oh, now let's say a new node is added. Let's say SN2 is added. So my hash function now changes from h equal to fn mod 2 to fn mod 3. Right. Now what would happen is now my hash values are not just 0 and 1, they are 0, 1 and 2. So now let's say after the alteration of my hash function, my K1 changed from so my K1's new hash value is 0, K2 key 2, K3 key 1, K4 1, K5 0, K6 2. Right. Now through this, the new storage node that for the new storage node on which the corresponding key would be present becomes like K1 remains as is from 0 to 0 here. So K1 used to be present on 0, but with the new hash function it is also on 0. K2 was present on 0, but now it is present on 2. K3 was present on 1, but K3 now is still present on 1. K4 remains unchanged. K5 was present on 1, but now it went to 0. And K6 was on 0, but now it went to 2. So if you see, when I added one more node, almost 50% of data place had to be changed. So K2, K5, K6, out of the 6 keys that I had, 50% of data required some movement. So because my hash function, when I'm writing something like this, my hash function to find the ownership of a key. If I'm using a function like this, if I'm using a modular function, it has a lot of problems, right? So this is something that requires a massive data movement, and here it's just 6 keys. Just imagine this was like 6 million keys, right? So then you would have enough data movement whenever you add a new node or remove or basically remove a node due to any reason. So given this, how do we solve this problem? So this is where consistent hashing comes into the picture. Okay. So did everyone understand the problem at hand? Right? Yes, no? How many of you didn't understand the problem at hand? Why data migration is becoming a problem? Okay. Samajh gaya? Good. Again, just one liner about it. Data migration, because our hash function is too static, because fn mod some function applied on the key mod n is what we are going for. So when n changes, a lot of hashes get reassigned. So the ownership of the node changes in a blink. As soon as the hash function changes, the ownership changes. So now this is where your consistent hashing comes into the picture. So consistent hashing, what it does is it helps you determine the ownership. Most of you might have already read about consistent hashing, but it's important to understand where do we use it. And this consistent hashing was made really famous by DynamoDB. So DynamoDB actually implements consistent hashing to determine the ownership of a certain key in your DynamoDB table. Which shard does the key belongs to? Right. So this is very important. So if you have not read DynamoDB's research paper, go ahead and read it. It's an excellent read. So let's say you have 1, 2, 3, 4 storage node, SN1, SN2. So here is SN1, SN2, SN3, and SN4. The ones in the blue are the hash values. So I have applied some hash function. My hash is being represented as a ring. It starts from 0 and it comes to 16. Right, so 0, 3, 5, 8, 10, 12. So these are values like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth. But every single thing that I have, let's say my SN1, I took some unique property of it, maybe identifier, IP address, whatever. I passed it to the hash function. So it would split the value in the range of 0 to 15, both inclusive. Right, so it split the value in that range. And in that same, when I passed my storage node SN1, SN2, SN3, SN4, SN1 value came out to be 3, SN2 value came out to be 10, SN3 value came out to be 5, SN1 value came out to be 3, SN2 value came out to be 12, SN3 value came out to be 5, SN4 value came out to be 10. Right. So this is where my storage nodes are virtually placed in this ring. Now I would want to identify where my key K1 belongs to. So let's say I have a key K1. When I pass the key K1 through the same hash function, I get value 0. So what consistent hashing says is the node which is immediately to the right of it has the ownership of this key. So the node which is immediately to the right of it is SN1. So my key K1 would be present on SN1. Okay. Let's say I have another key K2, and my K2, when I pass it through the same hash function, I got value 8. So now when I got value 8, again, with respect to considering, it says the node which is immediately to the right of it owns the key. So who owns the key K2? It's SN4. So when I'm doing a get or when I'm doing a put, so obviously first put and then get. Let's say when I'm doing a put, I want to insert key K1. So when I'm doing the key K1 ka insert, I would first find the hash value of K1. It would come out to be 0. Then I would find out the node to the immediate right of it. So it would come out to be SN1. So once I have SN1, I would use that connection to store the value. Right. So think about it like you can also think about like SN1, SN2, SN3, SN4 as 4 SQL servers. Right. And when you're inserting it, you want to fire inserts. You want to fire insert command on that. Right, but you would want to find out on which connection would I want to fire, or which database would I want to fire insert command. I can't fire K1 on all the 4 data because like then what's the purpose? So I want to fire on one, but who owns it? So you would run this consistent hashing. You would find K1 ka hash come out to be 0. You would find the database which is to the immediate right of 0, which turns out to be SN1. So you'd use its SQL connection to store the data, and then you'd fire insert command on that connection. So then your key K1 would be stored on SN1. Right. Now let's say you want to get the key, you'd want to get the value for that key. So you would again run through the hash function key K1, you'd get value 0. You would find the database to the right of it. You'd find SN1. You'll use that connection and then run select on that to get the value. Right. So again, consistent hashing is just here to determine the ownership. Right. Now comes the interesting part. Now, how does it solve the problem of doing minimum data transfer? So since all of this is just happening in runtime, what would happen is when I'm adding a new node in the system, let's say I've added SN5 here, right? So when I've added SN5 here, with respect to our logic, any key that hashes in this region used to go to SN1 before because SN5 was not there. But now that SN5 is here, all of these keys are now going to SN5. Right. So key K1 that was hashed at location 0 was going to SN1, but now when I inserted SN5, it got inserted here, and then now my ownership of key K1 changed from SN1 to SN5. Correct. With this, what has happened is, but if you see typically this is, if you just take example of cache, it is okay to have some cache misses at first, but if you'd want to still do the data migration of it, all you would have to do was this data, the data in this range, which used to go to SN1. When you're starting up a server, when you're starting up SN5, you would find all the keys that are responsible in SN1. You would take the snapshot of SN1, create SN5, and then add it to the cluster. As simple as that, right? Or if you're doing a downtime wala stuff, what you can do is you can just copy all the keys that hash to this location and store it on and basically populate it from SN1 to SN5, and then add it to the and then let it start the traffic. Right, but at the end goal should be simple. The keys in this region would now immediately start going to SN5, so that SN5 needs to have the traffic. But how is it minimizing the data transfer? Because all other ranges had zero impact when SN5 was added at this location. Right, this is where consistent hashing shines, because it just required us to, even after scaling up by 1, when we added one more node, we saw that example when we used fn of we use fn of k mod n. If n changes, a lot of things change, but here it becomes very simple. It's just f of n. There is no modulus whatsoever. So here, this only this much of only keys that are hashed onto this location are getting affected. Everything else remains unchanged. So ownership of this region remains with SN4. This region remains with SN2. No alterations there. Right. This is how it ensures that minimal data transfer happens. Right. Now, in the first case where we saw that if we just specifically take example of cache, in most cases it is okay for your cache to start with with no data, right? Because then what you would have is you just have few cache misses at the first. So the keys, when they go to SN5, and if SN5 is a blank node, there would be a cache miss, but then it would go to the database, get the value, update it in the cache. So in most cases, when you scale up your cache, you typically add a blank node in your system and not worry about like populating it. But if you'd want to do, if you not want to have any cache misses whatsoever, you would just read the data from S1, create a new node. You can use snapshots to automate to make this process faster, and then add the node to the loop. You would have a very minimum cache misses here. Right. So no alterations to other node. You would populate the data into neighboring node, the next one in the line, and add it to the ring. As simple as that. Okay. Did everyone understand? Did everyone understood this part? How can you do it? Either manually copy data from SN1 to SN5 for the keys that are hashes that are hashed in that part. Either incur cache misses. If you don't want to incur cache misses, copy data from SN1 to SN5. Instead of doing a live copy, you can always take a snapshot of SN1, start SN5 with that snapshot, and all the updates from SN that goes to SN1 should also go to SN5 for a certain time till SN5 is caught up, and then you terminate the connection. So then SN5 becomes independent. Right. So there are multiple ways to handle the data. Okay. Any questions here? Nice. Nice. Now, similarly, removal also becomes very interesting, because if my SN1 goes down, the key K1 that used to go to SN1 now goes to SN3. So the key range which was responsible for going to SN1 starts going to SN3. And similar to the previous case, you can choose, because when my SN1 is going down, it is not saying that I'm going down, and so SN3 please better copy the data, right? It just abruptly ends. So the keys that were going to SN1 just sees a cache miss for some time, but then it goes to SN3, it does not find, it goes to the database, then caches the data on S3. So eventually your SN3 would start would automatically start serving the traffic of SN1 and start serving the keys that SN1 used to hold. Right. So in most cases, this is how it would function. So this basically consistent hashing makes this thing very simple, because now even when SN1 went down, SN2, SN4 had zero impact whatsoever when SN1 went down. So if you'd want to do, let's say this was graceful, right? When you are deliberately taking it down, if you have time, what you can do is, if you're taking down, let's say you had SN5, SN1, let's say you're taking down SN5, basically graceful termination of it. So you can copy all the data from SN5 to SN1, as simple as that. So like run, like for all the keys in SN5, do a put on SN1, right? And then remove SN5 altogether. So you first block all the requests that goes to SN5, you forward the request that goes to SN1, and then you slowly copy the data there. Right? Basically minimal data transfer in both the cases. So you can extend the solution not just to caches, but also to normal SQL world, NoSQL state, embedded database, everywhere. But the core logic is something that would be a massive building block for you, where you can use that. Now, this basically concludes consistent hashing. One thing that I definitely want to end, it's easy for us to explain consistent hashing in theory, but the challenge comes in, how do you even implement this? Any idea on implementation of it?
I mean, binary tree is a good.
Very close. Binary tree, how will you do that?
I mean, you just see the nearest one. I mean, you go left or right, right? Basically, you see the maximum and you're done.
But how? But what would you store in the tree?
The hash values of those nodes.
Okay, you either go to the left or the right.
Yeah.
Okay.
And once you reach the basically the end, you're there. I mean, once you.
So all of the storage nodes would typically become the leaf nodes there.
Yeah, I mean, what I'm saying is, you want the maximum value. That is, I mean, you have, instead of searching in a binary search tree, you search for the value that is greater than it, but
correct
leaves one. Yeah.
So a very simple way of implementing this is using binary search. You can actually model it as a tree as well, but a very simple way is to just have all the storage nodes stored in a sorted array, which is sorted by the hash value, and just do a binary search on that. Right? Because if the key is not present, you can modify binary search to identify the first key which is greater than the key I'm looking for. Right? And these are standard operations given by any library, but it is equivalently easy for anyone to write that logic as well. So you can write that logic, like just find a key which is just greater than that. I've written a blog on this as well, on how do we implement consistent hashing. So go ahead and read that in case you are unsure about it. I've implemented it using binary search, and it's a very simple implementation, hardly like 100 lines of code to implement that. Like go through that and see how it is actually implemented. So binary search, where if the key is present, so I would always find the key which is and I'll just keep it sorted. I'll just leverage the fact that my array is sorted by the hash values and the storage node or the entity key, and then I would find the first one which is greater than the key I'm looking for. Okay? As simple as that. So that would work really well. So using binary search, it is extremely, so the overall complexity just becomes order log. That's it. Sure. Now the next part. How about having high availability? High availability is very critical for caches. So in most cases, if by the way, why do you think high availability is very important for cache? What if cache goes down? What would happen? And this is all out of real experience. Now, go on, what? You have seen this, now? You have seen this thing, right? Now, see, this is where experience matters. Like, so you would typically see, you typically think that cache is there to help be faster. Like you don't have to hit the database every time and then get the value and then return, right? So you'd always, so your cache is, in most cases, you would see cache as an aid, where it is helping you make your performance better. But what actually happens is your cache is, let's say you have an 80% or 90% of cache hit ratio, which means those many requests are not even going to your database. If that is the case, then your main database is actually under provisioned. So if someday your cache goes down, all of those requests are suddenly being bombarded onto your database. And in 99.99% of the cases, your database won't be able to sustain the load because it is under provision. Because obviously you would be provisioning the database for the load that it is getting. And if you have cache in between, the load is not even hitting the database, which means you are under provisioning your database. You're basically kind of over provisioning your cache. But when the day comes when the cache goes down, the requests that used to go to the cache or used to be served from the cache are now hitting your database. And every single of your bad SQL query comes to the light. And once the database cracks, it has a cascading effect onto API server. And if it is a microservice, it would have a cascading effect onto another microservice and then another microservice. And then eventually your entire system would go down. So a great way to avoid this problem is, even though you saw a cache hit, still transfer about 30% of your traffic to your database still, so that you are not under provisioning your database a lot. Like I've seen companies where the cache hit ratios are more than 99%. Like I gave you an example where almost all the data that we had was served from the cache. And we all have typically heard that, read to write ratio of database is like 1000:1. A heavily cached system is the one where writes are more than reads on the database. And this actually happens when you have a very heavily cached system where you see, we want to have great performance out of it. So you would typically have this system where your writes are more than the reads on a primary database. And this is not uncommon. This happens a lot. But when you have this kind of system, you are heavily under provisioning your database. So the day when your cache goes down, the request suddenly flows to your database. Every single thing that was served from the cache pre-computed is now hitting your database. Your SQL queries are being run on the database, or your database chokes, and then it has a cascading failure. So I think it is Uber who wrote about it, where they deliberately sent 30% of traffic to the, even though there was a cache hit, they would still send 30% of the traffic to the database. And this is how they ensure that they are not under provisioning their database. And they still see that their SQL queries are optimized, they are optimally written. Because like if you are not serving a lot of read requests from the database, then you would never understand that your SQL query is bad unless the doomsday come in where your cache goes down. Right, so something from the real world experience. So cache typically in aid becomes that one thing that should never go down. So in most cases, if you don't want your cache to fail, then what would you do is, if a node fails, it would lose out on the cache data because it is stored in memory, resulting in a lot of cache misses. So until your data is recached, it would continue to see cache misses, right? But how do we solve this? There are typically three ways. I forgot to write one more. There are typically three ways to do this, right? First one is read replica. So having a read replica even for your cache. Then read replica across a data center. Overkill, but still a practice, right? Where your cache becomes a really important component. And then a dump. So typically any cache that you have, let's say Redis or Memcache, although they say that they store the data in memory, they do a periodic dump of the data in local storage. It's like Redis does in RDB files. So you can invoke a Redis dump command. It would dump your entire cache and serialize it into a flat file. And when it is recovering or when it is rebooting, it sees that if the file is present, it uses that to basically populate the cache. So when your cache starts, it never starts from scratch. If it has that file, it uses that file and prefills the cache with that, and then it starts serving the request, which means you would not see 100% of the cache misses. You might still see stale data, but depending on the use case, you can configure it that way. Okay. Yeah, Anshuman?
Yeah, this Redis thing that you were saying. So this is part of graceful shutdown for Redis.
Graceful shutdown of Redis. Yes.
Okay.
So if you're doing a graceful shutdown, it would dump it into a RDB file and then basically gracefully shut it down. But there is even an option where in the settings file of it, you can configure how frequently would you want to dump the database. By default, it is 15 minutes or something. You can change it depending on how critical your data is. And then it would, and you can even make it synchronous. Every write that goes to Redis also goes to that RDB file. You can also configure that way. I've read it. I've not used it, but there is an option like that. So
okay, something like write through.
Right. Yeah. So something similar. So you can configure it that way, which
Okay.
means that even if your cache goes down and if it reboots, it loads from this basically from this flat file, and it does not really have to start from scratch.
Okay.
Right. So this way, this dump is that .rdb file. So every single cache supports a full cache dump. You can use that to not let your cache start from scratch and start from something. So it makes it's still not highly available, but at least it makes it reduces the number of cache misses that you have. Right. Then you can have read replica. If it is that critical, you can have read replica across your data center. Very overkill. I would not recommend that, but still I've seen companies doing that. But yeah, if your cache is that important for you, you can do that. But typically read replica would solve the problem, and add 2-3 read replicas and have a cache cluster around it would solve the problem. Okay. Okay. By the way, what did we just build? We just built our own distributed hash table. So all of the things that we discussed, although we started with distributed cache, but the kind of discussions we had, we actually built something called as a distributed hash table. Distributed cache, in any distributed cache in general, under the covers is nothing but a distributed hash table, where again, by the name, hash table is something that we saw, like jahan pe all the keys and values are stored and it is distributed. Now this is very important. Distributed hash tables are are extremely critical for any distributed decentralized system ever, like BitTorrent. Every single torrent file that you have downloaded comes through a distributed hash table. Like basically torrent is a classical example of DHTs. Any single distributed system or any single decentralized system you build has some kind of DHTs under the cover. It is a DHT under the cover. It has this thing. It would have to have, they are optimized for minimal data movement when nodes are added or removed. And where are they used? So DHTs are used, distributed file systems, DNS servers. People would definitely know it. Instant messaging, peer-to-peer sharing. If you've never read about BitTorrent's architecture, go ahead and read it. They're brilliant. And it's very simple. You would see how simple it is to implement your BitTorrent. You can build BitTorrent within a week. And a pura protocol into it. Right. So DHTs is something extremely critical. Wikipedia page for lots of information is there, but I'll obviously cover it. So we need to understand any distributed network that is there. So the idea of DHTs is very simple. You would have a data, you would apply a function, it would generate a key, and this key is nothing but a hash value, right? And then it would directly connect to that node in your distributed network. So this is how our cache even looks like. So you have a key that you want to store. You take a hash of it of key. You'd find a storage node. You'd go to the storage node and save the data. Like this is what a DHT is. So you have a distributed network. It might be connected, might not be connected, independent of it. So it could be peering, and it would do that. Do I have a slide? No. Okay. One architecture that is again very common here is to not directly connect to it, but let's say my key K1 points to a certain node, and if that node is not responsible anymore, but it would have the information that who could be. So it might just forward your request to another node which is responsible for that. So that is an optional feature that you can have. Like if this node is not anymore responsible, it would either send you, I'm not responsible, go ahead and basically connect to this other node, or it would indirectly forward a request to the other node. So there are multiple implementations of it. So it's very specific, but your DHT might choose to implement it or not. It depends on that. But if you see, there is no load balancer, right? So the load balancing is done through this distributed network. So your key is directly stored into this distributed network. So you, from this thing, you are identifying where do I need to connect to, and you are directly talking to that concerned authority. So it's like very simple. Bank hai, bank pay, you enter the bank. If the peon is there, right, you talk to the peon, and peon will actually forward you to a necessary counter. Right, this is a classical load balancer architecture, right? But if on a good day, if the peon is on the leave, you enter the bank, you pick any one at random, right? You go to that table, and that person forwards it to basically forwards you to the table which would actually serve your needs, right? This is a classical case where your peon acts as a load balancer, and where that other guy you picked at random forwards you to the counter where you should be heading to, right? So these are like two very classical distributed architecture, two architectures, one through load balancer, another one without load balancer, right? Okay. Decentralization. Okay. Load balancer. Okay. Network communication, P2P decides where your request should be forwarded to. Decentralization of accesses happens. You network protocols to identify server to go to. So this kind of architecture is something that I have specifically used, and it is very heavily used in system that operates at scale, where you don't really use a load balancer, but the flow goes like this. You go to the nearest, you basically go to the nearest one, and then it forwards your request to the one which is concerned. So it would either return you the address of it, or it would internally forward your request to that counter, something like that. So you can, so most of the architecture that you see in the virtual world, they are all, you'll find an example of it in the physical world, like somehow masked. Okay. So go ahead and Anshuman.
Yeah, so this so I just had one question on protocol. So I mean, this is a network protocol, but I had a different question.
Yeah, please.
So how do we decide which protocol to use, like TCP, UDP, or raw TCP? Can I even decide on those? Like when to specifically between TCP and raw TCP, like on sockets?
You can, I've used raw TCP, but you know, if you're working in an organization that typically deals with like period APIs, has a normal, you know, basic sort of application, then using a raw TCP becomes like too extreme. Why would you want to have that much of an overhead? In most cases, you would not need that, like in most cases. But if you're working at very high scale, where even that one, even that optimization matters, then you would choose that part, like implementing raw sockets and getting those things connected, handling retries and all of those fancy stuff. So I obviously at Amazon, I've used that. At Amazon, when I was building this thing, we used an architecture like this. We actually unknowingly implemented DHTs. We had something very similar. So we wrote a database which was precursor to DynamoDB. So I worked in that team where the database that we built was the inspiration to DynamoDB. So all the bad things, the database I was working on, all the bad things of that database was rectified with DynamoDB. Like basically, we were very infamous about it. We made a lot of mistakes, and which made DynamoDB possible. So we had an architecture very similar to this, where the request used to go to one server, that and if that server does not had the information, it used to give us the IP of the machine that we had to connect to, and then it used to return the IP, and then it went there. So there we used raw TCP connections to basically set up the connection and get it, because that was the only layer of performance that was left for us to extract. Everything else was done. So that's the last thing that you would have to do.
Okay.
But not something on day one. Definitely not something on day one, unless like you are basically Vitalik Buterin, you would want to like change the world, and otherwise no need. Yeah, Chandan.
Yeah, so as you mentioned about the peer-to-peer network, right? So how does the communication happens? Do they keep a track of all the IDs?
Yep, everyone would have to do it. Like, see, everyone cannot have information of every other node, right? So let's say just a very small example. You have torrent. Torrent is, let's say, geo. So every node in your torrent cluster that is distributed or decentralized in the world has information of about, let's say, 10 machines or basically 15 machines. If it got request of some file that it does not hold, it might have information about some servers who might be having like some sort of routing algorithm, right? And it would forward the request to that node, and that would internally check, does it have that information? And it would definitely have that information, and then it would give, and it would return back the information is where. So the place where it would find that information. Once it gets the information, then your main client would directly connect to that server and get the data, basically get the data. And this is typically how P2P network works. So you might go to the nearest person. Now this nearest could change. It could be random pick. It could be nearest. Then if it has the information, it would serve it. If it does not have the information, it would find the person that has that information. Right. And this is where the routing algorithm or the smartness comes in. Typically, if your network is very small, let's say 1,000 machines, every machine can have a copy of every other machine, or basically knows the existence of every other machine in the system. But if it's a torrent based thing, if you see like my machine could seed data, but what if my machine is like shut down, right? So my machine is not able to serve the file, although nodes in my machine might think that my server has that file, but my server is not up, right? So then they would have to redirect it to some other machine that might have that same file.
And the communication happens like normal, right? Like the way we
normal TCP connection. Yeah.
Normal. Okay.
But then the protocol to discovery will change. So the discovery protocol is what makes this thing special. So how would you discover how would you discover the true owner of the file that you're looking for? That's what is the game changer here. The discovery protocol.
Yeah. Thanks.
Sure. Yeah. This concludes it. One thing that I would definitely want you guys to think about is how would you implement word dictionary without using any traditional database, like not using MySQL, MongoDB, any database, but implement a word dictionary without using any database. How would you do it? Right. This is a problem statement. Word dictionary like apple, ball, A for apple, A se sare words, B se sare words, word and meaning would be there. And what you would have to do is you would want to support get, put, and delete operation. Something similar that we discussed. So here we are building our own storage engine. Like, so how would you build your own storage engine for this very specific use case, right? And obviously without using any database. So think about how you can, basically it's about building your own database using the most basic things available to you. Okay. Do think about it. Tomorrow we'll anyway be discussing a lot about this. This is something that we'll start with. And also apart from this, also think about the use case where how do you build cache on top of MySQL database, right? With the same set of throughput performance. One thing that on chat pinged was having large buffer pool. That's a good start, but it definitely can be made better. Okay, sure. Awesome. Any question? I think Rahul had a question. So basically this basically concludes. I just added a note about it. Read about routing of BitTorrent and gossip protocols in general. This is excellent read. Go ahead and like Google about it and read. It's really fun to understand. If you can put in time, do reserve 1 week of your time and implement your own BitTorrent. It's extremely fun to do so, and you'll learn a lot while building it. And while more importantly, when you're simulating a distributed environment on one machine, that becomes even more challenging. So bahut maza aayega usko. It was an assignment in my college time, so bahut maza aaya tha tabhi to. Now that I think of, I could have done it in a better way, but yeah, at least it was a great start for me. Okay. Yeah, so this concludes everything that I wanted to cover, and yeah, it does. And people who want to stay, want to leave. Rahul, you had a question.
Yes, sir. So you mentioned about the single point of proof. Explain the Redis one. I forgot that analogy. Can you
single point of failure?
No, sorry, just forgot. Can you go back to the slide?
Source of truth.
Yeah.
Source of truth. Wala. Okay. Source of truth. So source of truth, where you are using Redis as a source of truth, right? So the example which I explained was about having locks. When you are using Redis as your lock manager, because the data is only there with Redis. There is no other place where your data resides. It's only there on Redis. And so that becomes a source of truth because there is no other place, because typically your cache is never a source, or typically your cache is never used as a source of truth because it is always backed by a database. So your, let's say MySQL server is a source of truth. Then you have a cache, which is there to like make the performance better. And then you have your users who are talking to the cache. And then if it's not there, it goes to the database. Right? The example where we took was like, you'd want to use locking, or you'd want to solve the problem of writes before, or you would be reading stale data where it is not okay to read stale data, right? Where you have Redis as a source of truth, because that's when if you're reading stale data, you're giving wrong information to your user, because that is a source of truth and the data just got updated, right? So that is where you would be optimizing even for reading stale data. But in general case, reading stale data should be okay for caches. I hope that clears up, Rav. It does?
Yeah, it does.
Awesome. Sure. Any other? Yeah, Anshana?
Yeah, so on this side only. So how is this? I mean, minimal.
Okay, because SN2, SN for SN3 had to do nothing. Na? When my SN5 got removed, right? When my SN5 got pulled down or basically pulled out of my ring, what happened? All the requests that used to go to SN5 are now being forwarded to SN1. But did it have any impact on SN3, SN4, and SN2?
So it is minimal in terms of impact on the system.
Minimal in terms of impact, and even if we had to do transfer, let's say if the termination was graceful,
okay,
right? The data that had to be transferred was how much? Only the data that was catered by SN5 needs to be transferred to SN1. Correct? Baki pura data is intact. Right?
Correct.
And why and how is this less? Because like a traditional hash function works like this, right? You have some function operating on a key doing a modulus of n. Because when my SN5 got pulled down, suddenly my n changed. I was doing a mod 5, now I'm doing a mod 4. So there is a lot of data transfer that happened here with this example.
Correct.
Right? Now this got changed to this consistent hashing ring. Now with this, what happened is 2, 3, and 4 were sitting. We required no data movement on that front. But only SN5 data to SN1, and this basically this is why it's minimal data transfer. It's a bare minimum that is required, because when SN5 is going down, I have to put SN5 data to somewhere, and this data is just going to at one place. It is not distributed across.
Okay. So maybe this is a dumb question, but here we do, here we don't do a hash, right? Because we are putting it in a ring. So
exactly. We don't have to hash.
Okay. Hence, okay. Got it.
It's just going at one place.
Okay. So we don't do a hash over here, right? Then
yeah. All the keys directly go to that place. Because anyway, this, even if we apply the hash function, it would still come to SN1.
Correct.
Right, because hash function is just f of n. It is not f of n mod n. Or sorry, it is not f of k mod n. Right, because n, even if n changed, here there was no.
Correct. Got it. Okay.
Thanks. Yeah, Chandan?
Yeah, so a bit like I was reading one article where they had compared Memcached and Redis. So do you like so I just found few things which are available in Redis as compared to Memcached, like geospatial support and pops up. So like, have you ever used Memcached over Redis for any particular region? Okay, no.
Always Redis. Redis always wins.
Okay, but
there is no specific advantage of using Memcache. Basically Memcache got an early mover advantage. It was probably the first one that operated at scale, and then Redis came in and swept the world.
Okay, but they have mentioned like the multi-threading support is available in Memcached.
Redis also does very well. Redis also is highly concurrent.
Okay.
I did benchmarking for our use case specifically, but I never found a very genuine use case to like use Memcache.
Okay. Yeah. Thank you.
Like there might exist some use case, although they say threading and all, but I've never found concurrency issues with Redis. It does a fantastic job.
Okay. Yeah.
Yeah, Prabhat?
So like in this form of consistent hashing, like I can see like we can have skews, right? Like for example, if SN1 like
nice, yes.
yeah, all of the like traffic of like SN2 and SN both will go to SN3, while like we have another SN4 which may like handle that traffic of SN1 like equal. So like I have seen this optimization where like
Virtual servers.
yeah, so like we have virtual kind of servers like we but like there I got confused while reading upon it is like we so like one implementation was kind of we used k hash functions and like for each and every server say like SN1 we use k hash function and like those hash function will give k values.
Yes.
And those and we will do again %n and since like this SN1 will be represented by those k points, right? And like this someone like commented that like this is pretty hectic to maintain k hash function, and instead of it like we can create a list, say like if SN1 is represented by an integer say k, then we can first maintain a list k plus 1 to say k plus something n, and then hash each of those values.
I'll actually give you a very simple answer to that. Not even worry about k hash functions. Like just imagine if you can manually place a certain SN1 or 2 matlab jo bhi storage node hai, at a certain specific position in the list.
Okay.
Right. So you are manually changing the position of the storage node, like basically doing some sort of doing a variation of range based partitioning. Having a k hash function, adding virtual server nodes solves a problem. To some extent it does, to some extent it definitely does, but it has a lot of implications. Not that big of an implication, but still thoda sa ho jata hai. But you can do that. But a better way to do it is just translate or transform this problem into range based partitioning and not use hash based partitioning.
Okay, so like the problem then boils down to we have to divide the circle into fixed ranges. Say
you can start with fixed ranges, but there also you'd still be playing on that part that my keys are uniformly hash in the ring. But you would anyway have to do that, right?
Yeah, so like if we distribute the circle into fixed ranges, then one of my requests will fall into one of that fixed range, and that fixed range will be assigned to one of the servers, one of the actual servers.
Yes. मतलब हमेशा फिक्स आधे पे स्प्लिट करते जाओ उसमें, मतलब जहां पे बढ़ गया वहां पे बीच में डाल दिया, something like that, assuming that your keys are uniformly hashed across the ring.
Yeah, that we assume that the hash function has that property of like randomly assigning.
But अगर अपना random function is like return for every time, then तो वो ना होगा, right? But in some cases that you'd have to pick A over B. In some cases, virtual servers do help. मतलब it's not that cumbersome to maintain, but then your application logic becomes a little tedious. But आजकल तो libraries and also it's okay. But your first approach should always be using virtual servers, and then optimize it using range-based partitioning ka variation, which is something that we can discuss.
And like in a real world, like how do you select that hash function? Like
murmur hash, suna MUR.
So like famous hash functions we can take.
There are 5. So MD5, murmur, these two work really well. So I implemented Bloom filter using this very hash function. So we also did something very simple, because while implementing Bloom filter, you also need multiple hash functions, na?
Yeah.
Very similar to this, right? So वहाँ पे भी you need multiple hash functions. So murmur hash, MD5 hash, and lsec को नाम था. Those 3 hash functions we used.
And like I have one more question where like we were discussing the availability of cache. So like in availability of cache, like we have like different strategies of caching, right? Like read through, cache aside. So like just like one question popped in my mind, like when in read through cache strategy, we go through the cache and ask for a value, and if the cache doesn't have that value, the cache itself asks from the database for that value.
Yes.
So like if that cache node goes down, does it mean that we will not be ultimately like our request from the API server will fail?
No. If your cache is down, your request will directly go to database. So you will hit the cache, it would give you an exception.
Okay.
Once there is an exception, you would go to the database and get the data, because you can't let your user not see or not access the data.
But if the node of the cache is itself down, so it won't be giving.
But exception that timeout error, network error,
Yeah.
kuch to aega na?
Yeah.
Right. At least if a node is down, you have initiated a request, you will get a timeout error, you will get a network error that a node is not available or basically could not resolve IP. Some network exception would come in.
Then our API server will handle this exception and
exactly. Okay. Any other? Chalo. Any other question?
Regarding the implementation of distributed keys, consistent hashing, sorry. So we will store, like what exactly we store in the binary search, binary tree?
Binary tree, I'll give, I have not implemented it using binary tree because वो थोड़ा cumbersome था. What I found much simpler was this. I'll show you. सब लिखा हुआ है, बहुत पढ़ा है पहले जिंदगी में. Consistent hash. See, the idea is very simple. Let's say I'll just tell क्या है, एकदम simple है, ठीक है? Let's say I have 5 storage nodes, and I actually took example of storage nodes to make it like very one-on-one. Okay, so I have 5 storage nodes A, B, C, D, E. Each has its IP address. Okay. Now hash function takes my key, whatever the key is given to it, it encodes it, converts it into byte sums, and then mod 5. So some hash function. So the function sums the byte present in the key and then takes a mod with 5. Because 5 storage node, ideally I should have given a len of storage nodes for now. Okay, but okay, mod 5. Then upload path, what I'm storing there is this. Yeah. Okay. So my hash function is add node. So when I'm adding a storage node, so my storage node had just host and port. That's all I had. So when I'm doing an add node, what I'm doing is I'm finding the position where I would want to add. I'm keeping 2 arrays, like one array of nodes, right? I'm having one array where I'm storing nodes. I'm having another array where I'm storing keys. The keys are hash keys of all the storage nodes. So the length of these 2 arrays is exactly the same. So the number of nodes I have in the system and the array of the keys that I have in the system, because her node ki ek key. For every index I, the node and the key mapping is one-on-one. So node, this storage node A and key K1, ये दोनों मतलब storage node N1 मतलब storage node A की key is first, मतलब at every ith index there is this one-to-one mapping of it, right? When I'm looking for something, I'll be always looking in the underscore keys wala array, this keys wala array. So I'll be doing a bisect. Basically I'll be finding in the first key. So the place where the key should be inserted is nothing but the value which is just greater than my current key with that I'm looking for. So I'm just finding that index, and in that index I'm just inserting my node, because this is where my node should go in, this is where my key should go in. On that index I'm just inserting it. So you just have to maintain these 2 arrays and you are sorted with this, and then just have one binary search for logic. Like this thing. This is exactly how it would look like. So when you're doing a put file, you would have a massive hash space. So you would have B over here, K over here, and E over here. So these are 3 storage nodes. And this is the file where it needs to go to, or these are the file and the hashed where the location where the file is hashed. Given this thing, I would find the rightmost here. So now my array, when I have 3 storage nodes, which is like B, K, and E, my array size would be just 3. I would not want to have the entire ring to be stored anywhere. My storage, my array size would be just 3. I would have 2 arrays, one of nodes and one of keys. Both are sorted by keys. Okay, and then I'll just do a binary search and find it. That's all I have to store. Okay. Really very simple implementation. देखो इतना सही code है यार. Like when I added, उसमें से comment ज़्यादा है. Like when I'm adding a node, just error check here, hash space is full. Other than finding a hash, finding the position where I want to insert, then collision occurred, and then I'll do some data migration if I want to do. Or since I'm adding a new node, I want to do data migration and all if I want to do. And then I just insert the node in the array and I'd insert the key in the array. It's just that at a specific index, and this index is nothing but given by the binary search. That's it. तो राहुल एक बार बस पढ़ लो, बहुत सिंपल सा implementation है, nothing major. Really very simple implementation of it. And I was just really wondering how do I actually this happened in Swiggy interview. I applied Swiggy in 2017, 2018, and that point again like pressure, my fashion experience 1.5 year ki, I'll do this consistent. I was really happy. I was asked to design distributed cache. I said this thing and I'll do consistent hashing. Then the interviewer asked me, how will you implement consistent hashing? Again, same theory, ring. But then he said, how will you actually implement it? I said ring. So nodes there. Then I said linked list. He said, would you be storing, let's say hashes 2:128 key hash space? I said no. Then I was like really stuck. And that day I came home and I said, I want to study ki kaise karte hai. And then I went through it and I found a paper which implemented it using this array. And like this is such a neat way to do it.
By the way, like I have found like recently one more hashing, highest weighted hashing, like which is much more simpler to implement and like gives like a similar performance to consistent hashing.
Highest weighted hashing.
It is also called rendezvous hashing.
अच्छा rendezvous, हाँ ये वाला हाँ.
And like it's so simple to implement, like very simple.
मैंने देखा नहीं है ये मेरे reading list में rendezvous hashing.
So like this hashing is actually being used in the GitHub load balancer. So like GitHub has open source like load balancer since they run their own data centers. So they use this hashing in their load balancers. So that's why like I came to know of this.
चलो आज की रात तो sorted है आपकी. Nice. ये मेरे reading list में न जाने कब से पड़ा है. मतलब but once वो हो गया consistent hashing तो उसके बाद में फिर वाले लगा कहाँ ही दूसरा पढ़े. But हाँ, it was long time. चलो आज खत्म करते इसका.
And like Arvind, like here we have discussed consistent hashing with caches, but like this same thing can be used with sharded databases as well.
Sharded database, हाँ, मतलब basically caching too. You can replace caching with anything, with load balancers, API server, sharded database, anything that you would like. It is not really limited. It is not really limited to anything. मतलब basically consistent hashing is a concept. You can apply it at anything you want. Like basically load balancer में consistent hashing लगा सकते हैं. Right? You'd be मतलब your request कौन से node पे जाएगी serve होने को? Consistent hashing. Anywhere where you want to define ownership across a set of homogeneous nodes, consistent hashing would be your answer. मतलब could be your answer.
And like in real life scenarios, like what have you seen? Like does API server handles this consistent hashing or like
API server. So you would have because you can implement consistent hashing as a library. All it needs is to maintain that source of truth. कि मतलब ये सारे elements है, right? So there has to be one metadata information जहाँ पे all of this information is stored. But yeah, typically this is what I've seen. So it basically polls it randomly and down to is always down. But when we scale up explicitly, we update the metadata table first so that every server gets that information. Okay. Chalo. Any other question, guys? Nice. Chalo. Thanks a ton. See you guys tomorrow. Do think about two things: implementing word dictionary and MySQL as a cache. Okay.
Like isn't like word dictionary already a distributed hash table?
Think बनाओ ना जैसे बना सकते हो बनाओ. It's all open. However you want to do it.
Can you use tries for that in Python?
I want database. I want to have database. मतलब let's say it's 1.5 terabyte big.
Yeah.
Try फट जाएगा तभी.
Yeah.
Just take it to extreme and see if your solution would survive. मजा आएगा. मतलब it's a really fun exercise. This is something that I did in my BTech. तब बनाया था and I really strongly remember कि वो it helped me to learn so many things when I was like very young. मैं बोला ये तो example लेना ही लेना है to build word dictionary on your own. क्या क्या कर सकते हैं, कैसे डिजाइन कर सकते हो उसको. Just think about it. मजा आएगा. चलो. Thanks guys. See you tomorrow. Bye bye.
Thank you.